for us, and also the very important chapters of rotational kinematics and rotational dynamics. So what you have done, just to put it in perspective, when we started this semester, we were doing kinematics, if you remember, right? So we learned about how to use the kinematic formulas when you have a constant acceleration. That's what we learned. And the first couple of chapters, in fact, the first 3 chapters that we did pertain to kinematics. And then we entered Newton's law when the force came into the picture. And because force is mass times acceleration, and forces can vary, so can accelerations, or vice versa. So we went away from the constant acceleration assumption that we made for kinematics to a scenario where acceleration actually could vary. But all of that was for motion along a straight line, or for motion like a projectile, which is motion in 2 dimensions, meaning x and y. What we haven't done is a systematic analysis of what happens when things rotate. Because when you have rotating objects, very similar stuff happens, okay? So all the kinematics that we did, they come in handy. And all the dynamics that we have learned using Newton's second law come in handy. The language is just a little bit different. And as long as you understand that, these chapters shouldn't trip you up. But we are obviously considering physics that is more complicated, and therefore it is important that you don't slip off, because the chapters I'm going to do with rotational kinematics and rotational dynamics after what I discussed first, which is momentum conservation, these chapters are critically important, and they often break your back in exam 3. So I'm letting you know ahead of time that please be cognizant that this stuff is nothing to fear about, but you should understand what we are doing and be aware of how to deal with it, because it is a learning curve, and it comes late in the semester, so you have less time. Now, one of the things that I wanted to discuss first is the idea of momentum conservation. So what does this mean? It probably doesn't mean anything to you, but to a specialist like me, a physicist or a mathematician, momentum conservation is an extremely important term. So let me just tell you in plain English what momentum conservation is all about. You have learned about Newton's third law. And Newton's third law tells us that action and reaction occur in pairs, right? So one of the examples of Newton's third law can be this bottle of water is made out of molecules of all different kinds, polymer molecules. There's plastic, which is not a good thing for the most part for the environment. But anyway, so this glass of water, which has all these forces interacting, literally not even countable number of forces interacting between all the molecules all over this bottle, nothing eventually happens with all these interactions. This bottle is not, going off somewhere. The bottle is not doing anything weird. The bottle is just sitting there. It's a boring bottle. Okay? Why? Well, we know all the forces are acting because the forces have to act. We know that atoms and molecules, they interact. We are made out of them. So what's going on, which is so interesting and so special, by which nothing is happening, it's just sitting there? Well, the point is that all these forces taken in unison, vectorially added up, gives you a net force of 0. Okay, so that's a direct consequence actually of Newton's third law, because if a molecule here is pulling a molecule there, that molecule is also pulling this molecule, and so on and so forth. Everybody is pulling everybody, or everybody is interacting with everybody more generally. And as a consequence of that, what you have at the end of the day is that the vector sum, if you could add it up, the vector sum of all the forces here add up precisely to 0. Now, when you think in that terms, it's pretty amazing that it adds up precisely to 0. But this also is an example of what we are about to do with momentum conservation. So we can have a scenario then that all the forces, when added up, let me think in terms of simple one dimension right now. I can put a vector sign, it doesn't really make a big difference. But the net force, let's say, is 0. Think about that bottle, think about the table, think about the chair, think about anything that's just sitting there. And then you can imagine, well, this is happening in 3D, so I'm going to put a vector sign on it. So that's a bit more general, right? Now we know, so it's easy. So it's easy in a way to satisfy this condition. We can almost take anything that's just sitting there and we say net force is 0 because it's not doing it. There's no acceleration. So if there is no acceleration, that necessarily means, since mass is not 0, that necessarily means that the net acceleration that's involved must also be 0. Okay? So this leads to an interesting conclusion, a rather complex conclusion actually. So what is acceleration? When we think of acceleration, the definition of acceleration is how velocity changes over time. So that's like a general definition of acceleration. And acceleration is a vector, as we know. So we put a vector sign here, and we say it's delta v, vectorial change in velocity over some time delta t. And we can say this is the net acceleration. And then we must say that this is therefore the net velocity change. Why net? Well, we're talking about that bottle, or we're talking about something big. And therefore all kinds of accelerations and velocities are involved. When I say net, what I really mean is that all those added up vectorially, you can't do it by hand. At the very least, you need the world's most powerful computer. Even that will crap out. But if you could do the calculation, this is what you should find. So what it means then is to say, if this thing is 0, right, then this quantity here in the numerator must also be 0. That's what it means. So we generally therefore end up, since let's consider mass because we are actually talking net force. So we should be able to write that m times delta v net, which is the net change in velocity, must therefore be equal to 0 if there is no net force. Again, the important point is there is no net force. So at this point, we can stop the discussion and we can go home and say, okay, fine, this is something I realized, that if there is no net force on something, then m times delta v net, vectorial addition of velocities before and after, essentially should come out to 0. So over a time delta t, this delta v net must add up to 0. But there is a consequence of this, and the consequence of this is the conservation of momentum, which is what this really means. But there is a simple way to use this. So we'll now drastically simplify our discussion. First of all, we will define a quantity that we will call momentum, which we thus far haven't carefully defined. What is momentum? Momentum is, by definition, mass times velocity. So clearly momentum is a vector, because velocity is a vector, and mass is a scalar. Mass is not a vector. Just so that you know, sometimes momentum is written as small p, not large p. Large p is pressure, small p. Okay? So why is the definition of this m times v needed? We already know what v is, we know what m is. Well, m times v turns out to be an important quantity for dynamics situations, because if you have something moving at a velocity v, let's say you have an electron which is super tiny moving at a velocity v, and you have a truck moving at a velocity v. While the velocities of both these guys, the electron and the truck, may be exactly the same, if you get hit by an electron, you wouldn't even know. If you get hit by the truck, you'll probably be dead. There's a difference, life and death difference. So the fact is that the fact that the electron is extremely light and the truck is extremely heavy matters here. So momentum, therefore, takes into account the mass component here. So therefore, it's mass times the velocity vector. It turns out it has a very important use for us. So in this case, because there is no net change in momentum, if there is no net force, so no net force implies no net change in momentum we can write in plain English that momentum before a process, let's say a collision process or an interaction process, must be equal to momentum after if there is no net force. Just to be specific, we can think about a collision in which there is no net force. So momentum before collision and momentum after collision. In general, you can replace a collision by interaction. A collision may be a collision between two masses, a collision between two cars, a collision between two planets or satellites. A collision is something that we know what it is. But interaction is far more common, right? Interaction happens all the time. Atoms and molecules in this very room, in air, they're interacting all the time. So this is a little bit, the term collision is very specific. That's what we'll deal with now. But it doesn't have to be the only thing that we are learning about, just so you know that. So now that we are simplifying the problem to that of collisions, momentum before collision, momentum after collision, because there is no net force, we need to be a little bit clear about what we mean by collisions. There are various kinds of collisions that we encounter. So very simply put, there are three kinds of collisions. One is called an elastic collision. This is the simplest kind in a way, but not necessarily the simplest kind in terms of calculations or collisions. Then we can have what are called inelastic collisions. And then we have completely inelastic collisions. Naturally, completely inelastic collisions would be a very special case of inelastic collisions. So when we talk about collisions, we must therefore discuss these three different guys, and that's what we'll do next. And therefore, the discussion of collisions now become an important aspect of what we are trying to do. When I say elastic collision, there are two things that you must know. A, if there is no net force, then momentum is conserved. Let me write in shorthand. Momentum is conserved. There is no net force. It turns out, in the simplest scenario, there is a second thing, and that is kinetic energy also conserved. Mind you, I'm not bringing in potential energy into the picture. It just complicates things quite a bit, so I'm leaving it out. I just want to understand the physics of these systems at the very simplest level, because that turns out to be good enough. The trick about doing science is that how much can you simplify a problem? Because our capabilities are very limited. We can't solve big problems easily, in fact, if at all. So what we try to do, as you may have observed so far, is we are almost always trying to take a problem, make it as simple as possible, yet preserve its most important features, and then see if we can solve that problem. And then we construct our way back and see if we can get the big picture. So in this case, it turns out for elastic collisions, these are the two conditions, two sets of equations, therefore, that we must be dealing with. In inelastic collisions, it turns out that momentum is conserved, but kinetic energy is not conserved. So only A is there. In completely inelastic collision, we have a separate version of A. I'll call it A prime. So here, yes, momentum is conserved and kinetic energy is not conserved. But plus, the masses get stuck to each other. Simple example, I throw a chewing gum at you. Not a nice thing to do. But the chewing gum will get stuck on you. It's an inelastic collision because the masses get stuck. So these are the three cases that we'll do. So let me repeat what we have just done. First of all, I've pointed out that if you have no net force, then there has to be momentum conservation in the problem. What do I mean by that? Break it down. If you have two bodies, if you have interaction between two bodies, then interaction, or in a simpler case, collision between the two bodies, comes down to the problem of momentum before the collision to momentum after the collision being the same. So that's what I just wrote down, momentum before and momentum after being the same. And then I pointed out that there are three different kinds of collisions that we must consider. And in these three different kinds of collisions, the first one, the elastic collision problem, is where you have two sets of equations. One is for the momentum conservation piece, and one is for the kinetic energy conservation. The second, only momentum conservation. This is the most general case. Most collisions happen to be inelastic. Completely inelastic collisions are basically elastic collisions in which the two masses get stuck. So let us now see what it is that the elastic collision is all about. So I'll just first consider the elastic collision. So let's take a very simple example where we have two masses that are gliding along. So I have a surface here, there is a block here, and there is a block here. Let's say this block has a mass m1, and this block has a mass m2. Okay? I don't know what m2 is. Suppose this guy is coming along at uniform velocity. No acceleration, because acceleration means there is a force. There is no net force in our picture. So it's just coming along for simplicity at a uniform velocity. And let's call it velocity of mass 1, v1, initial. Initial means before the collision. And let's give it a number such that we have an idea of what kind of values here may be at play. Let's say it's 1.2 meters per second. And let's say m1 is 0.340 kilogram. I took this problem from a book a long time ago, so I'm just using those numbers. So it turns out that this is before collision. After collision, this is what you see. So if you were to take your video camera and record, this guy was at rest. So V2 initial is 0. M2 was just sitting there. Nothing was happening to M2. So now what happens is, actually from your own experience, everyday experience, you can see quite a few things may be happening. V1 final, and of course if M2 was at rest and M2 has been hit by M1 and there is no friction, then you expect M2 to actually pick up some velocity that way because it's been hit by somebody coming from the left to right, and therefore it will have a V2 now final. I don't know what V2 final is. Okay? So I don't know what M2 is. I also don't know what V2 final is. I only know that M2 was at rest. I only know that M1 was moving towards M2 at a velocity of 1.2 meters per second. I know the mass of M1, which is 0.34 kilogram. These are the things I know. All right? So now what happens is, after collision, it is possible that M2 is moving to the right and M1 may also be moving to the right. It is also possible that M2 is moving to the right and M1 may be moving to the left. How do you know what is true? that might depend upon the values of M1 and M2 involved. So you can immediately see that the problem is not that simple. All right? It's a very simple problem in the way it's set up, but in terms of consequences of what might be going on, it's not super simple. So let us pursue this problem. So first I can already apply momentum conservation. So let me apply momentum conservation, which is to say momentum before is momentum after. So momentum before is going to be M1 V1 initial plus, let me just write it down anyway, M2 V2 initial. This is 0 because V2 initial I've already told you is 0 because M2 was resting. M2 wasn't moving. And then I should be able to write M1 V1 final plus M2 V2 final. So that's an equation. And this equation comes right out from the momentum conservation law. But I have another weapon. And the next weapon is I have kinetic energy conservation also I can follow in this super simple problem. How do we do that? Well, it's very simple. We just take kinetic energy of M1 before collision. So that would be M1 V1 initial square plus kinetic energy of M2 before collision. This would be 0 because V2 initial is 0. So this term actually is 0. And so this is before, and after I have half M1 V1 final squared plus half M2 V2 final squared. That's what I got. Okay. So as you can see, everybody has a half, so there's nothing special about the half, so I can get rid of that. All right. I can't get rid of anything else. So I've now optimally simplified it. But I can collect my M1 term. So there's an M1 term on the left side here and an M1 term on the right side there. So what I can do is I can write M1 and then I can write V1 initial square minus V1 final square. I can write that. And then on the right hand side, the surviving term is going to be M2 times V2 final square. Now this is a wonderful problem because I have two unknowns. I don't know what M2 is and I don't know what V2 final is. V2 initial I know. And I have two equations. I have a momentum conservation equation and a kinetic energy conservation equation. So because I have two equations and two unknowns, the problem actually turns out to be nicely solvable in this simple case. So this is a squared minus b squared, which means we can write it as a plus b and a minus b. So therefore I should be able to write this as M1 V1 initial minus V1 final and V1 initial plus V1 final. And this is M2 V2 final square. Let's call, okay, we don't have to call this anymore. So now what I can do is I can actually divide this guy, divide this statement here. Question? Okay, I can divide this statement here by this equation here. And that's nicely doable. So let's see, I had a nice, I can write it in the following way here. I can write it as M1, there should be an M1, V1 initial minus V1 final, right? I've taken this term on the left side is equal to M2 V2 final. So now you see if I divide, that equation there, so let me write it out fully. M1 V1 initial minus V1 final times V1 initial plus V1 final, and here I have M2 V2 final squared if I divide the left side by the left side of this, so I divide one equation by the other, see, something very simple emerges. So this is now the left side, and the right side would be M2 V2 final. These are just two equations. We have done this kind of division of equations before, and that's exactly what I'm doing. In fact, when we calculated, when we were doing the car on the inclined plane going in a circle, we did similar things. So you see, these two guys will cancel, these two guys will cancel, and M2 will cancel, and one of the V2s will cancel. So now we have this beautiful problem where we can write that V1 initial plus V1 final actually must be equal to V2 final. It's really cute. There's no mass dependence. We have in this case, in this simple problem, we have managed to eliminate mass dependence and actually come to a conclusion that is rather useful. And depending upon the values involved, V1 final is how M1 is going to go, right? After collision, M1 can go to the right or left. So V1 final can be right or left, positive or negative, depending on this value and that value. So at this point, we have actually calculated V2 final, which we didn't know. But we still have one thing we don't know. We don't know what M2 is. So we now need to find out what M2 is. So V2 final is now determined. We had two. I told you I don't know what M2 is. I don't know what V2 final is. So how do I know what M2 is? Well, I can do something quite straightforward. I can actually take what I have just learned, which is this thing here, and put it in my first equation. And then what happens is that I have M1, V1 initial is equal to M1. Remember, V2 initial is 0. M1 V1 final. So this is the momentum plus M2 V2 final. And this is of course that equation there. So I can now write this as M1 V1 initial is equal to M1 V1 final. But now I can substitute for what V2 final is from this derivation here, which means I can write this is plus M2 V1 initial plus V1 final. In other words, I've just replaced V2 final here by what I have just found. So you're probably wondering, why am I torturing myself? So I won't torture myself anymore. I'll just give you the answer, because now I know everything else that needs to be known for me to determine what M2 is. And so I take this to the left side. So I have M1 V1 initial minus V1 final divided by V1 initial plus V1 final. So that now is how I'm able to find M2. And therefore, both the unknowns that I were after have been found out. So just to give you the numbers, because I started giving you the numbers, it turns out I didn't give you the V1 final. That V1 final, by the way, let me just write it down. I used a number of 0.66 meters per second, I think. So if I have these numbers in these formulas, I end up with a V2 final from the calculation here of 1.86 meters per second, and an M2 of 0.987 kilograms, just for the sake of finishing that part of the problem. One of the things you might have observed is that doing these problems take a bit of time, especially if you have an elastic collision problem, because in an elastic collision problem you have to use two sets of equations, and that's just one dimension. So if I give you an elastic collision problem, for example, where you have something coming like this, let's say a car or a block or a puck is coming like this, and maybe hits a puck here. This is a two-dimensional problem, right? Depending upon how the masses are shaped, a lot of things can happen. Similarly, these problems can easily get very complicated. So elastic collision, although elastic collision is one in which you have more equations to deal with, but it's relatively easy to imagine them becoming very complicated. Just to give you an example, when you look at ice skating, especially ice skating when couples are involved, you obviously realize that they're choreographed very carefully such that they come out the way it's supposed to come out, with the right moves at the right times, and so on, with the right speeds. It's pretty much a momentum conservation problem. In fact, a great deal of dance choreography is very precisely done, and all the timings and everything is fixed by relatively straightforward physics, such as momentum collision. A little bit more complicated than what I've just shown you, but that is the kind of physics that's applied for these kind of ice skating shows. Let me give you another example. I'll give you an extreme example. I'll give you the example of a completely inelastic collision. Let me use another chalk. This chalk has run out of steam. A completely inelastic. So this is the third case. Why did I skip the second case? I skipped the second case because the second case of simple inelastic collision, where you only have one tool, momentum conservation, turns out to be the hardest one in real life to be able to work out. Yes, Brett?
Where did you get the equation about the M1
this equation is the same as that equation, the momentum conservation equation. So all I'm just doing is replacing V2 final by what I have just derived. Okay? So I'm substituting, because I know what V2 final is now, so I can get rid of it. That's how I find it. Okay? Any other questions? Okay. So let us say a completely inelastic collision. Let's say you have a rifle. Here you have a trigger, and the situation before is that the rifle with the bullet in it, they're just sitting there. Nothing's happening. So clearly, the initial momentum would be zero because there is no speed, there's no velocity here. Now what happens, let's say, is that you fired the rifle. So you take the rifle and you fire it, and you have a little bullet here that's going that way. All right. So momentum before collision and momentum after collision should be the same, because this is really a problem where interaction happened, like a Newton's third law situation, but there is no net force acting on the system. There are internal forces, but no net external force acting on the system. So this is the situation after. And what you expect should happen is that because this was at rest before, so momentum here initially was zero, momentum after, again, should also be zero, because momentum should be conserved, right? There is no net external force. So if this bullet is going to the right, then intuitively you should expect that the rifle now will recoil a little bit as you fire the bullet. In fact, that's indeed what happens. When you fire a rifle, you have a recoil. So let's see if we can quantify this problem a little bit so that we have some understanding of the numbers. So let's give us some numbers. let's say the rifle mass is big M and the bullet mass is small m. Let's say big M is 3 kilograms. And small m is quite tiny. It's 5 times 10 to the minus 3 kilogram. The velocity of the bullet, let's say, is standardized, so you can read it off. And let's say that's roughly 300 meters per second to keep numbers simple. And you can, so let's call it V bullet. And the question may be, what is V rifle? So this is rifle, this is bullet, just so that we are very clear as to what's what. So you can see this is a completely inelastic collision problem, which means that you cannot use energy conservation, kinetic energy conservation, because that's what I wrote on that A prime condition in my table. Completely inelastic collision is going to be this case here, and in completely inelastic collision, you can only say that the momentum is conserved. The reason why it's completely inelastic was because the masses were together before or after. Same thing happens, by the way. So in a bomb explosion, so when you have a bomb that explodes, the reason why it's extremely complex to study a bomb explosion process is because typically when it explodes, it gets broken down into a very large number of pieces. Momentum is conserved, by the way. So if you took the velocities of each and every piece and their masses and reconstructed them back to calculate the total momentum after the explosion, the answer should add up to 0. So this is why you may know that there is a missing piece or there are missing pieces. So these are very complicated problems to solve in real life, but the principle used is something as simple as what we are learning today, which is momentum conservation. So let us move on. So this problem is therefore a really whittled down version of an explosion problem. So if I tell you, for example, that a bomb explodes and separates into 2 parts. So if you know their masses, or if you know the ratio of their masses, you should actually be able to find the ratio of the velocities, because m1 v1 final plus m2 v2 final must equal to 0, because initially the bomb was just sitting there. All right. So momentum conservation therefore gives us initial momentum is 0, and then we have so this is going to be the bullets situation, and I don't know what's happening to the rifle, so I will not assume anything. And then there is a V rifle, or I call it a VR, I think. Yes. Okay. So this is momentum after, this is momentum before, and if you do the calculation, it turns out that VR will come out to minus 0.5 meters per second. So it has a small recoil velocity. Now let me just show you why kinetic energy conservation doesn't work. It's very easy to see. Nothing was moving before. The thing was at rest. So what was the kinetic energy before you fired the rifle? 0. Kinetic energy is a positive quantity. You can't have a negative kinetic energy, because half mass times velocity squared. Velocity squared is positive, mass is positive, and half is positive. So therefore, if you're going to sum up the kinetic energies of what's going on with the rifle after you're fired, which means you've got to sum up the kinetic energy of the bullet and that of the rifle, you add them, you can't have 0 anymore. So kinetic energy before, which was 0, and kinetic energy after, which is a positive quantity, can't be the same. And that's the reason why kinetic energy, in this case, conservation, will not work out. So in all inelastic collisions, completely inelastic collisions, energy conservation will fail. But momentum conservation may hold up. The condition that made this calculation possible was basically because the masses were together before, which is a special condition, which is an extra condition we had. That is the one that allowed us to solve this problem. There is another problem, which is a very common problem. So I will just sketch it for you because it's a little tricky, but the rest of it I'm going to put it on the homework on the coming Monday. By the way, I've assigned a homework that is a short fuse homework. It's not much work, but this is work over the weekend. It's due on Monday as usual. And then coming Monday, we'll resume our natural cycle. So this problem is called a ballistic pendulum. A ballistic pendulum is typically used to study the properties of a gun or a bullet, typically. Can be used for other things too, nothing special. So the idea here is really simple, but the physics is so beautiful I can't tell you. So the idea is that you have a block of wood, let's say, big block of wood. Let's give the mass a name, MW, okay? And you hang this block of wood with two very light, essentially massless strings. Now what you do, you want to study the properties of this, let's say, bullet, and you fire this bullet, and the bullet comes, and actually after a while it ends up getting embedded somewhere over here. So the bullet essentially gets stuck to this wooden block. So, and we can give it a velocity v. This one was just hanging there. This one was not oscillating or anything. This was just hanging there. And you can have a video camera, just like Rance has over there, to figure out what's going on. Okay? So now what happens is that the bullet comes and gets stuck. And as the bullet gets stuck, this one, which had no energy before, no kinetic energy, it will actually now swing up because it is like a pendulum. It has nowhere else to go. It's going to swing up. So now you see what happens is that if you were recording with your video camera, you should basically see that your block has gone up to some height. So the block originally was, let's say, at this height, and maximum height the block achieves may be this height, and therefore the distance by which the block has been raised may be some quantity h. So if you are video taping this, you can read off your tape what this h would be, all right? If you know the h, and if you know the mass, you can actually calculate the potential energy associated with the pendulum's rise, mgh. That allows you to calculate the velocity with which the two masses, the bullet which is stuck to the wood, started moving just after the bullet hit this. So you know that velocity because mgh must be equal to the kinetic energy here by energy conservation. So this part is very simple. So it gives you this velocity here of the post-collision problem here, from which you can infer whatever it is that you want to infer. So let me just quickly sketch it. So momentum conservation alone initially means you have a bullet mass and you have a bullet velocity, okay? Let's call it v. And then finally, because it's a fully inelastic collision, you have bullet mass plus the mass of the wooden block, I call it big M, times some big V. This is the velocity that the system acquires after the bullet got stuck here and started to move, because initially it wasn't moving, and now it starts to move, and it has no way to go other than to rise up. Okay? So, and this is an inelastic collision, so you won't get very far trying to use energy conservation alone on this part of the problem. So small v is something that you can infer if you know big V, because small v is going to be mb plus mw divided by mb times big V. So that's the bullet speed that you may want to measure in a typical example. So, but to measure small v, everything else being known, you actually need to measure this quantity, big V. How do you do that? Well, I already told you how to do that. So let me just show you very easily. So I told you that when the bullet gets stuck to this block, you have kinetic energy. This kinetic energy makes this thing go up. So therefore, I should be able to use energy conservation for that part. So post-collision, this is not pre-collision, this is not the first part of the problem, but post-collision I'm going to use energy conservation. So it's a very nuanced problem where initially there is no energy conservation because you have inelastic collision. I only use momentum conservation, but post-collision I use energy conservation. So just immediately after collision, I should have mass of the bullet plus the mass of the wooden block, because the two are stuck together, times, I already told you, I assume the velocity is big V. This must be equal to mb plus mw times g times that height h by which the pendulum must rise. And now it's a trivial problem because these two guys cancel out, the mass doesn't matter, and therefore v squared is simply 2gh as it should be, which would then imply that this velocity is 2gh square root. So now you see I can measure the velocity of the bullet just by measuring that height h, and therefore from above I have mass of the bullet plus mass of the wooden block divided by mass of the bullet times big V, and that big V is 2gh square root. So that now becomes your formula for discovering the velocity with which the bullet must have been fired, or the bullets fire at typical velocities. So here you can test the velocity of the bullet, and from which you may be able to make inferences about what kind of bullet might have been used in a particular case. Any questions so far? This stuff is not easy, by the way. So the whole game about elastic and inelastic collisions can get quite tricky. So I really want you to be well prepared when I ask questions about these things, including in the quizzes, because I will ask questions on this in the quizzes coming up. I won't be spending too much time on it because it's not a very long issue to discuss, but it is important regardless. Let me now move to something else. I'll actually start off with the fundamentals of rotational kinematics, as I said. But before we go there, we need to do some house cleaning. The house cleaning involved is defining something that we haven't defined yet. And you probably have wondered about it, at least unconsciously, but certainly nobody has asked that question in any big way. So you see that thus far we have been very happy to take blocks, give it a mass m, and then pretend that the entire mass of the block or the ball or whatever is actually just a mass point, meaning it has no extension in space. Thus far we have done just that. And it has worked out beautifully, because all the things that we needed to do so far works out very nicely if I consider a block or a ball or whatever as a mass point, until we reach a point where this mass point's size and shape can actually become somewhat important. So let's say, for example, that if you have a disk. Imagine you have a dime or a quarter of a disk. You know darn well that this disk has a certain size and therefore a certain extension in space, and mass is distributed over this extension in space. Now suppose you want to rotate this coin, and you immediately figure out that if you're going to rotate this coin, let's say you put it at the tip of your finger, and this is your finger here. Whether you put your finger here to rotate it, or whether you put your finger, let's say here, to rotate it, the rotation actually would be different. We know very well that if I put my finger here, if I try to rotate this, it's going to be far more wobbly. And if I put it smack in the middle, and if I rotate it, it's going to be more stable. So what I'm trying to say is that the axis of rotation here being in the center, and the axis of rotation here being off center, makes a difference in how the rotation takes place. What difference does it make? Let me ask you guys, do you think that if I change the axis of rotation, keeping everything else the same, the energy of the rotating coin can change? What do you think? Take out a coin. I'm assuming you guys have some coins. Any coin would do. Just make a mess, drop some coins so I can loot your coins. No, I'm kidding. But take out some coins and try to rotate them right now. Some of you guys are so lazy, you're just sitting there. Come on, man. Take some coins out and rotate the damn thing. What happened? Couldn't find a coin? What kind of people are you? You have no money, you're dead broke. All right. Let me tell you what happens. It turns out that the motion actually is quite different depending upon where you put your finger here. So it turns out then that this motion will be a lot wobbly than this one, and it may well be that the energy of the rotating coin in this case may not be the same as the energy of the rotating coin in that case, where it's in the center. So this means that we have to be very careful in dealing with solid objects that are rotating. Just to give you another example, you observe that in this door here, the axis of the door is here, right? Because the door turns about this point. And if you are smart, which I know you are going to apply a force here to open the door. Now, if I'm really nuts, I'm going to try and apply a force here to open the door, and I'll be working all day and the damn door will not open. So the point is that where I apply a force when there are solid rotating objects is a big deal. You know, here, for example, it's a complete waste of metal to actually have anything here, really, because nobody would want to apply a force here to open this door. It's the most inefficient thing in the world to do. However, if you apply a force at the edge, it's trivial. So it turns out that the axis of rotation plays a big role. What I need to do first is define technically what center of mass is. And center of mass has a very technical definition. It's a mathematical quantity, really. So in general, center of mass along x-axis is what you'll get if you take every mass point and its location in the x-axis. Every mass point not a single guy left behind, and sum it over the total mass. So this, of course, is the total mass again. So that's X center of mass. Likewise, because it's a three-dimensional object, we have a Y center of mass, where every mass, mi, yi, and this is divided by m, has to be taken into account. And likewise, there is a Z center of mass, which would be sum over I, mi, zi over m. Okay? So center of mass, therefore, is a quantity that we can actually calculate. Now, you might be wondering, how the hell am I going to sum up the mass of every particle? Well, Newton solved this problem a long time back, and Leibniz as well. They basically said that you don't have to do this nitty-gritty. You can actually do an integration. I know you guys don't do integration, but this is a problem that is relatively simple to solve by replacing the sum by an integration and using the tools of integral calculus. So that's doable. We're not going to worry about it, but I want you to not worry about it, because this is something that we have known for the last 400 plus years. So at the end of the day then, we can actually calculate the center of mass. Now, having known the center of mass, what does it give me? Well, it actually gives me some tremendous advantages, and we will come to that. But before that, we need to set up another little toolkit. I'll go over this on Tuesday, but let me just give you a very brief preview. Suppose I look at my coin or my disk and see it turning. Okay? In all the cases in the past, we have only considered the angular speed omega, which is really the circumference 2 pi r over the time period t for a full rotation, this being r, is equal to constant. So this is what we did before. Okay? But now what we are going to do is we are going to say omega is no longer a constant. So in other words, omega can vary. So in other words, the speed at which you are rotating, the angular speed, can slow down, can speed up. We allow for these kind of nice, interesting possibilities. So what that means is that we can think in terms of how this omega will change in time, just like we have thought about how velocity changes in time, delta v over delta t, right? We had it here somewhere. And delta v over delta t is acceleration. So delta omega over delta t is also an acceleration, excepting that this is called the angular acceleration. It's denoted by alpha. Angular. It's not an angle, by the way. It's called angular acceleration. So angular acceleration, because this one doesn't have any units, right? It's in radians. So this is simply going to be delta omega over delta. Delta omega is 1 over second unit. I'm sorry.